All right, so I think tonight we're going to finish up chapter 6. I just want to make sure we cover all the bases with it. I did grade the 3 assignments that you've done so far, projects, homework type of thing. So the grades are out there right now, out of 10 points for each one of those. So we'll have more. There'll be more coming. Okay. So you'll be able to see your overall grade and everything like that. Yes.
Are we able to see the answers? So like how we did, where do we do incorrectly?
Well, we could spend a little time on that. Maybe next time, if you have a question about which one, yeah, we could spend a minute on that. Just go over the answers. So.
Okay, because I'm not sure. Like I didn't get full credit, but I'm not sure which part I didn't do perfectly.
Okay, what are you referring to, the homework or projects or what, the test?
Oh, I'm talking about the homeworks.
Oh,
the
okay.
Homework.
Yeah, I mean, the last homework you did okay, I think, didn't you? I think 9.8 or something out of 10 or something.
Yeah. I wonder what's wrong with that point too.
All right. I probably just took off a little something because of a slight little error. It was just a
Okay.
computational error or something. Yeah,
Okay.
I don't think you have to worry about that.
Okay.
You're on the right track pretty much for everything. All right, so don't worry. Most of the mistakes I saw were just slight little errors, nothing major. I didn't see anything major. Steve, the same thing with you. I saw a couple little minor things. So, and I think it may be because maybe you were moving pretty fast through it or something. I don't know.
The last homework actually took me a little longer than I expected. Yeah, it took me like over 2 hours to do. I mean, just computer projection. Yeah, I mean, I was being extremely careful, but
okay. All right. Okay. I was hoping it wouldn't last that long. Do that homework, but that's fine. That's fine. Whatever it took to do. So any other questions or anything about our schedule? Or I think today we were supposed to start chapter 7. Is that right? Is that what the schedule
Yeah, you said
says?
so.
Yeah. So
let me see.
I think today was chapter 7. So is that right?
Yeah. It says section 3.4 and 7.1.
3.4. Oh, okay. That probably has to do with scatter plots, maybe. I don't know. I thought I already went over that, didn't I? Have empirical rule and analyzing data. I went over that, right?
Professor, I'm having some trouble hearing you. Han, are you having the same trouble?
Yeah, I didn't hear anything.
You didn't hear anything?
Yeah, I think, Professor, I think when you turn your head from the microphone, it's a lot less sensitive.
Okay. Then I'll turn one eye to the left. I'll move over here. I believe I've covered this already. 3.4.
Oh yeah. You know, it says Chebyshev's rule, so we did cover that.
I've already that was what I was thinking in the beginning, but now as I going through it, I think I've covered it. So next time we'll cover 7.1, and what was supposed to be next time? 7.2.
7.2 and 3, and the concepts that are named are normal distribution and calculating probabilities.
Okay, so we're gonna so I'll be able to cover all of that next time. Won't be an issue. I do want to finish some of these sample questions in chapter 6 today. Just want to make sure you're solid. Oops, I turned my head again. I don't want to do that. So I think we covered a couple of these last time on page 201, right? 201. I think we did 6.454 and 6.55. Is that correct? And I think, Steve, you had mentioned something about 6.55. You did it as a binomial instead of as a Poisson.
Oh, right. Yes, I remember that.
Now, the reason why the numbers came out almost exact is because the rate, which is actually, by the way, in 6.55, crash rate, 1 out of 100,000. In the binomial terms, that would be the probability of quote unquote success. Okay, and it's very small. And then the number of successes in this question would be 50,000, right? 50,000 would be that. Yeah. So we're talking about a very large number of trials and a very small probability of success. Under those conditions, the binomial and the Poisson will give pretty much this an equal answer. But if the number of trials is smaller, then they're going to diverge a little bit. They're not going to all be that much different, but they're going to diverge. They're going to be different enough that you know the difference. So 6.55 is perfectly fine to use the binomial for. It's no problem. But many Poisson type problems don't give you a rate or a probability. It's not giving you that information. It's giving you the expected value, the expected amount. Okay. That is that lambda in the Poisson. If that's all that's being given, then you really have to work with the Poisson and not use the binomial. Okay. And I think there's an example in here, which we'll go over. Now, 6.56. Let's go over that one. Let me read it. Again, I'll read it straight ahead. Bill has, here we go. Bill has to sell 3 more cars this month in order to meet his quota. Tonight he has after dinner appointments with 5 prospective customers, each of whom happens to be interested in a different car. If he has a 30% chance of success with each customer, what is the probability that he will meet his quota by tomorrow morning? All right, so he needs to meet his quota, he needs to sell 3 more cars. All right, 3 cars basically. All right, so this is a binomial because there's a probability of success, 30%, right, 0.3. And there's only 2 outcomes. Either he gets the customers or does not, right? So for those 5 prospective customers, either they are going to buy a car or they're not. So this is, and it's a fixed number of trials here, right? There's 5 customers. So this is a binomial. All right. So go ahead and work this problem. You have hopefully you have a calculator with you, and just come up with your answer. I'll give you like a minute and a half to do this. This is just a one binomial probability that you have to calculate in this case. What I had saved. All right. What I'm going to do is I'm going to put you guys on share the screen. Show you how you can do this easily in Excel. Find it. Here we go. All right. So to do this, you just set up an X on one row and a probability of X. Another row. Now there's 5. This is number of trials, so you always start off with 0 for binomial and just do 1, 2, 3, 4, 5. Right. Then in here, you're going to type in binom, right? Distribution, DIST. Open up a set of parentheses. Number of trials is 5. Right? Probability of success is 0.3, right? So you could, I guess in this case, you could just type in 0.3. All right. So number of successes. I'm sorry, that's the wrong number of successes. Now, number of successes would be the X above it. And then the number of trials is 5. Actually, you could just point to the last number and put a dollar sign next to the I to keep it fixed. Just squeeze it in there. Probability of success is 0.3. And then it says cumulative, right? And the answer would be false, right? F-A-L-S-E. I believe that's what they want. Right. And then you can simply copy this all the way down. You get your probability distribution. All right. You can always double check by the sum across the probabilities to make sure you did it correctly. All right. So there it is. And the P3 is what you want, which is this number right here. Okay? It's very easy to do this. You can answer almost any of these questions, any binomial this way. Now, 6.57 is saying, what if instead of each customer getting a car, suppose that they're all interested in the same car. We use the binomial in this case here. So you have to think through, is this a binomial? Is this still a binomial, or is it something else? Now remember, in the binomial case, the trials are independent of one another. And if they were all interested in different cars, they would be independent, right? It wouldn't matter which car a particular customer was interested in. But if they're competing with the same car, and then they sort of go elsewhere if somebody gets that car, is this truly a binomial? And if you say no, you have to give me a reason. So you have to think about what makes a random variable a binomial, and what is it in this case that does not make it a binomial?
I would say that it's not binomial, and it seems like this problem, if they're more than one is interested in one specific car, then that would mean that it like wasn't using replacement because you're lifting a car out of circulation in this case. Whereas in the other situation, since they weren't looking for the same car, it was as it like taking one away would have no effect on it. So it was like there was replacement.
All right. Let's assume that 0.3 is a probability that comes from thousands and thousands of people. What cars there? All right. So let's assume that that probability is not going to budge much. Is there another reason why this is not a binomial?
I think the events are not independent.
Yeah.
All right. Go give me more detail on that. Why aren't they? Well,
Like-
obviously they're competing with the same, right? But there's one
Yes.
other. All right, that's true. But there's even a better reason. That's true. I would definitely say they're not independent. Certainly that's one of them, but there's another reason which I think brings out this point even better. Now it says 3 of them. It didn't say all 5 of them, right? The other 2. The other reason is because the number of trials aren't fixed.
All right.
Because let's say if only 3 are interested in the same car, but the other 2 are interested in other cars, we don't know how many trials this is going to take to sell a car, right? To sell 3 cars. Number one, it could be that the 3 people who want to buy a car are all interested in the same car, or it could be that 3 people who are interested in buying a car are interested in 3 different cars. It is possible, right? Because the other 2 people, we don't know about them. It's possible. So the number of trials is uncertain ahead of time. So this is not a binomial for that reason too. That's the one I wanted you to focus on. That's an important part of a binomial. Sometimes a random variable could be something like what's the probability that, let's say what's the probability that somebody buys a car in the car lot, right? Let's say people just going into the car dealer, and maybe it's just a slow night or something, and it's really tough for nobody's buying a car. Question is, what's the probability that that first person buys a car? Well, the number of trials could be any number of trials, right? It could be the first person walking in the door, it could be the 10th person walking in the door. See what I'm saying? So I want you to think about the number of trials too. You know, binomial's fixed, absolutely fixed. But you're right about the independence. That's certainly true. But also the number of trials obvious also could change in this situation. It could be different. Okay, to get all three. It's possible that the number of trials is 3 out of 3, right? Could be number of trials of 3. You just happen to hit three of the people who want different cars, and they all buy the car, right? So the number of trials could change. It could be 4. The number of trials could be 5. The number of trials, right? Could even, right? It's possible. Any of those are possible, right? And if these other 2 people are also interested in that same car, then the number of trials is just 1, right? As soon as somebody buys that car, everybody else is gone. That's possible too. So both those things, I think, are broken in that case. The independence and the number of trials aren't certain. All right. Let's look at 6.58. During the 2009, boy, this is an old book, right? Published in 2011. During the 2009 tax filing season, 15.8% of all individual U.S. tax returns were prepared by H&R Block. For a random selection of 3 tax returns, describe the probability distribution for X, the number in the sample whose returns were prepared by H&R Block. Definitely binomial, right? Because they want a random selection of 3. So 3 is the number of trials. That's fixed. Probability of H&R Block doing any tax return is 0.158. Okay, that's fixed. And anybody getting a tax return done is independent of anybody else, right? We're assuming there's independence there. May not be true, but assuming that. And we want to describe the probability distribution. Well, if you're going to describe it, you might as well do it in Excel, right? And just put it right through. So what I'm going to do in this, I'm going to copy this in the next couple cells down right here. And since n is 3, number of trials is 3, I'm just going to put 0, 1, 2, 3. And then I'm going to copy this formula down. I might as well copy it, right? Copy it down to here. Right. Okay. Now let's look at the formula. The first position is what? First position is the number of successes, right?
Success.
Yeah. So, and then the next one would be what? No, it says I8. Well, it can't be I in this case. It has to be G8, right? So we have to change that to G.
G.
Yeah, because the G is the final value in the probability distribution. It's 3. And I have to point to G now instead of to I. I was the previous problem. All right. And then probability of success, I have to change that. 5.8. Now I can copy this over. And then do a total here. Probability. And then I'll do equal sum here. Just to verify the probabilities are correct. There we go. There's my probability distribution. Okay. And by the way, if you want to round these to 3 decimal points, I'm just going to do quite a few columns here. You could just simply right-click, format number. I'm sure you've done this before, and do decimal places, 3 decimal places. Now, all of my probabilities are in, I didn't want the X's in 3 decimal places, by the way. So that I'll change to 1 decimal point for both of those. All right, and same thing up here. I'm sure you've worked with formatting before, right? With formatting cells and yeah. Probably not the most efficient way of doing this. All right. So these are the probability here. This is a probability distribution. So in this case, the probability out of those 3 that none of them were done by H&R Block was 0.597. By one of the 3 is 0.336. 2 of the 3 claims is 0.064, and that for all 3 of them is 0.004. Right. So this is the way of describing the binomial, right? This is a binomial. All right, you see what I did? I copied the formula down, then I just changed a couple things. Yeah. Okay. I'm sure there's a more efficient way of doing it than the way. All right, let's look at 6 points. Let me see the next one that I got. 6.59. 20% of the population of Maryland describe themselves as binge drinkers. 20%. Geez, an entire state. All right, for a randomly selected group of 5 Maryland residents, use the appropriate statistical table to describe the probability distribution of the number in the sample to describe themselves as binge drinkers. Right, meets all the criteria. Emil? Trouble with my, there we go. All right, so what is the number of trials here?
5.
5, right? So I can actually probably
Use the first one.
use the first one, right? That's what I'm gonna do. All right. All right. So what do I need to change here? I need to change, what's D4 again? Well, that's fine. I4 is what? That's fine too. That's the number of trials, right? 0.3, that has to change, right? Or does it change?
0.2.
0.2, right? 0.2 gets changed. All right, so we change that to 0.2, and that's it. That's all the only thing we change in this problem here. Do have to copy this over. So the probabilities, all the probabilities are correct. Here it is. Rounded to 3 decimal places. The last one says 0, but obviously it's not 0. It's something smaller than 1 in 1,000. Okay. But for all intents and purposes, we'll leave it at 0. All right, any questions about that? That's good. So these are easy to identify. You see what I'm saying? Binomials easy to identify. All right. Look at 6.60. You tell me what type of probability distribution this is. A company has installed 5 intrusion detection devices in an office building. The devices are very sensitive, and on any given night, each one has a 0.1 probability of mistakenly sounding an alarm when no intruders present. If 2 or more of the devices are activated on the same night, the intrusion system automatically sends a signal to the local police. If no intruder is present on a given night, what is the probability the system will make the mistake of calling the police? All right, first of all, is this binomial?
It appears to be binomial to me.
Okay, go ahead.
You're basically looking for the probability of, if you consider, you're looking for the probability of two successes. You know, each of the devices, or yeah, at least two of the devices go off.
Uh-huh.
So at least on superficially, it seems like it's just binomial.
Uh-huh. Okay. So what is the probability of quote unquote success in this case here?
0.1 for each device.
Uh-huh. Okay. So you're saying there's 5 devices
Yeah.
and the probability of one of them going off is a binomial situation, right? 1/10
Right.
probability. Okay. Going off when there's no intruder, right? That's what the probability is referring to.
Right.
It's a mistake, basically. It's going off when there's no intruder. Okay, so how would you solve it using the binomial?
I would set it up as you had set up those other ones, only the number of trials would be 5. And the probability would be 0.1. Probability of oh no, wait. Yeah, the probability of success would be 0.1, and you'd be looking for 2 or more successes.
Okay. All right, so I'm changing the individual probabilities, right? Oops, that wasn't right. Copy. All right, so I'm changing the individual probabilities here. So it's at least 2, right? At least 2. So it would just be the sum of these two, right? Because these are practically 0. So 0.081, the answer?
Right. Yeah. I think so.
Well, because for it to go off at least 2 or more, so it could be 2, it could be 3, it could be 4, or all 5 go off.
Yeah. And
well, the probabilities of 4 or 5 going off are practically 0.
Yeah.
So it's basically these two sums here. The answer is actually a little bit above that, you know, if you just did it using the formulas. But if you said 0.081, you're pretty close to the right answer if you simply add up these two cells here. And actually, you could, if you wanted to, because Excel knows the answer, right? You could simply take the sum of those. You can just put the answer over here. You could just do equal sum and just run your cursor over from 2 through 5 here, right? That's probably the best way of doing it. And it still rounds to 0.081. Actually, the answer is 0.08146. So it is rounding correctly. 3 decimal places. Right? If you wanted it to 5 decimal places, you know, you could just reformat that to 5, and it should be 0.08146. Just see if that's correct. Yeah. All right. So you simply would do the sum over those cells, and you get your answer. That's it. So with Excel, it's pretty easy to come up with your answers. You don't have to worry about formulas or anything. You just set it up, run your cursor along the cells that you need to add together. So you're correct. This was a binomial, right? Definitely binomial. All right. And the number of trials is the number of devices, right? The number of the devices, and each one is independent of one another. That's the other thing that you had to make sure of. Each device has to be independently, its functioning has to be independent of the functioning of the other 4 devices for this to be binomial. And did it say that in here? It doesn't really say it, right? but it should. It should
Mhm.
say it. That was the one thing that was missing from this. It didn't say that. How about 6.61? A mining company finds that the daily lost work injuries average is 1.2. The local union contract has a clause requiring that the mine be shut down as soon as 3 workers incur lost work injuries. On what percentage of the days will the mine be operational throughout the day? So they say it will be shut down as soon as 3 workers incur lost work injuries, right? Because they think the mine is unsafe at that point. So basically 0, 1, or 2 injuries is considered to be acceptable, right? For the mine to continue to operate throughout the day. So how would you do this? Is it binomial? Can you use binomial in this case?
Uh,
First of all, there doesn't seem to be any number of trials, right?
right. Yeah.
So that's one of the requirements for a fixed number
Yeah.
of trials. It's not there. What's the probability of success? Do you have any idea?
No, no. And you said in the beginning of class that Poisson's usually used for when you just have an expected number, not necessarily a probability.
Right. The 1.2, we don't know. We would have to know the rate, a rate times the number of people that created that 1.2. We don't have that information. So we cannot, this is a case where we cannot do the binomial. We just don't have the information to do it. But the Poisson, we can. Now, because lambda is what? Lambda in the Poisson formula is, in this case?
I can't remember what term lambda is. Let me look it up.
1.2.
Yeah, the mean.
Right,
Expected
1.2.
number.
1.2. All right, now, like any other discrete probability distribution, we can set up a probability distribution here. Let's see if it does work. Let's see if Excel does this. If not, we can go to Minitab. Okay, and we can now. It asks us to do 0. X is 0, X is 1, and X is 2. That's what we need, right? That's all we need. Oops. Change this. Formatting. All right. 0, 1. So we have these 3 possibilities, right? For X. That's what we need to add up, the probabilities for these 3, right? Because X is 3 or more, it shuts down. So we're not interested in those. We're only interested in X is 0, no injuries throughout the day, or 1 injury, or 2 injuries. And that's it. We just have to know what these 3 probabilities are, and then we add them up and get our answer. Do you agree with that?
Yes.
Yes, because X is the number of injuries during work-related injuries during what they call lost work injuries. And the only way that mine continues to function throughout the day is if there are fewer than 3 of these. All right, let's see if they do Poisson here. So I'm going to just type in POI. Hey, look, it's here. Hi, yay, yay, yay. All right, good. So it's there. I just start typing in Poisson and POI, and it gives me it. So I'm going to type in the distribution. Now it says X. X has to probably be referring to what? It's referring to the number above it, right? The X value. So I'm just going to type in D12 in this case here. And comma, the mean, that's the lambda, 1.2. So really, lambda determines your answer here, right? And cumulative, we're going to say false, right? Because now we could do true here and just put in 2 and get our answer, right? Do a cumulative one, put 2 in.
Right.
Want to try
Yeah.
that? We could try that, right? to get our answer. But let's do the whole
Sure.
probability distribution this way. Copy the formula over. Now, by the way, this is only part of the probability distribution. If you did a total at this point, it should not be equal to 1, right? It should be less than 1,
Right.
right? So if we did a sum here,
Yes.
I'd be surprised if it was actually equal to 1. Right? It isn't. But that's fine because we're not, I mean, if I created a bunch of x's going across here, eventually it would approach 1, right? As x approaches infinity, it's going to, yeah. So we're not worried about that. All right, so we can get rid of this here. Don't need it. Oops. And the answer is going to be the sum of those 3 probabilities here. Actually, we already did it, didn't we? This sum here is going to be our answer. All right, 0.663. That's not right. I think we just did it a second ago, didn't we?
Yeah.
And I think, yeah, it's that 0.8, whatever it was. That's our answer. But if we wanted to do this as a cumulative answer, right, we could have just, let's just use this cell here. We could have just did the Poisson. All right, and then we put in 2 here, right? 1 point. We put in the largest value that we want to. The probability we want is the probability that x is less than or equal to 2, right? So we're going to put in 2 there for x, for a cumulative, and we're going to say true for here. So we're doing the cumulative. It should give us the same answer. Okay? So this is definitely, you could just do the cumulative and get your answer. And you just put in 2 for x because it's this here. I'm just going to put it right here. This is the probability that x is less than or equal to 2. All right? And that's 0.879. And this would be the cumulative. By putting true in for cumulative, you get that answer automatically. All right? By plugging into 2 here for x. You clear about that? You didn't have to do this, by the way, right? You could have simply put in your 3 numbers and add them up. That's the same thing. So it's not that much easier to use the cumulative function here. So that's a good example of the Poisson, right? Poisson gives you the answer. All right. So that's why I wanted to show you that question. Let's go to the next page and look at 6.65. Fred and Emily are among 50 finalists in a lottery in which 5 winners will be randomly selected to receive a free vacation in Hawaii. Using the see, they're even telling you what distribution to use in this case. Using the hypergeometric distribution, determine the probability that exactly one of these 2 individuals will win a free vacation. So basically, the population is 50. All right. Out of those 50, there will be 5 winners, absolutely certain. All right. So 50 people, 5 winners. What they're doing here is they're saying, okay, Fred and Emily are among those finalists. So we have a sample of how many?
2.
Right. And we want to find the probability exactly one of them will win a free vacation. So the number of successes is going to be 1. Now the question is, why is this not a binomial? First of all, what's the original probability of success?
10%.
10%, 5 out of 50. Now, once somebody is selected, right? Once somebody is selected, it changes the probability of success in this
Right.
case, right? So this is not, this is, the probability of success is not fixed. This is a hypergeometric. Now, you could do approximate binomial here if you wanted to. You got pretty close to the answer. But you might as well use the hypergeometric to get the exact answer. Now, the formula for hypergeometric, if you want to look at it, is on page 200, towards the bottom, right, of the page. You'll see it. The big N in that formula, it's a ratio. So the numerator has two combinations that are multiplied by each other. The big N represents the size of the population. In this case, it's 50. Small n is the size of the sample, in this case, 2, right? S is the number of successes in the population. Well, that's 5. And X is the number of successes in the sample. Well, that's what we are being given, right? But it could be anywhere from 0, 1, or 2, correct? Out of a sample of 2,
Right.
you could have none of them winning, one of them winning, or 2 of them winning. In this case, they just want to know what's the probability of one of them winning. So we're going to make we're going to make X equal to 1. So the numerator, the first combination says combination of out of how many? What is S? Number of successes in the population? That's 5, right? So out of 5, we want 5. Out of 5, we want how many? We want 1. So S
1.
X should be 5, 1, right? That combination there. S is 5, X is 1. The next combination is N minus S. N is 50, S is 5, so that's 45. And the bottom part of that combination.
Wait, Professor, isn't it 50 minus 2?
No. S is the number of successes in a population. 5.
Right, but S, excuse me, sorry.
Yeah, N minus S is 45, 50 minus 5. The bottom is N minus X. We have N 2, X is 1, so that'd just be 1. So the two combinations on the top, the way we would say it is 5, choose 1 is the first combination, and the other one is 45, choose 1. If you ever have a combination with 1, where we say choose 1, then it's simply the number on the top. All right, 5 choose 1 is 5. Right? Isn't it true? 5 choose 1 is 5. And 45 choose 1 is 45. So the numerator is 5 times 45. The denominator is N choose N. N is 50. N is how many?
2.
2, right? So it's 50 choose 2. So the numerator has 5 times 45. The denominator, if you figure it out, it's 50 times 49 divided by 2. So it's actually 25 times 49. And if you do the math, I came out, go ahead and do the math. Tell me what answer you got for this one, this question. Oh, did you come up with something? Round up to 4 decimal places. For probabilities in general, if I don't ask you, just round to 4 decimal places.
I got 0.1837.
Right. And Han, did you get that too? Good.
Yeah.
All right. There's your answer. 0.1837. You can match it to the back of the book. Your book has the answers to the odd number questions. You see it matches. So they tell you in this case here, it's hypergeometric. The next question, 6.66, they don't tell you that. But you have to see that it is. All right, so let's read number 66. 7 of the 15 campus police officers available for assignment to the auditorium in which a local politician is to speak have received advanced training in crowd control. So it's 7 out of 15. If 5 officers are randomly selected for service during the speech, what is the probability that exactly 2 of them will have advanced training in crowd control? Let's do that one first. Now, the probability, the initial probability that they have a police officer or a campus police officer has crowd control training is 7 out of 15, right? But that's going to change, right? Once the police officer is chosen, right? And it's not, we're not choosing it, we're sampling without replacement. So that probability is going to change quite a bit. So that's why the hypergeometric will be used in this case, all right? But go ahead and do this. See if you can do part A, and then we'll do part B. And I'm going to double check to see if, while you're doing that, I'm going to see if Excel does the hypergeometric. If it does, then it'll save you some time. Well, yeah, it does. It does do the hypergeometric, which is interesting. All right, so I'm gonna do that with the computer while you're doing your thing. Actually, how many are? Right? All right, we only need 5. So go ahead and use the formula. I think you have a couple different possibilities here. Sample size. Number in the sample. What's the answer? Actually, that's just all right. That's right, it's 5 in the sample. Sample size, the number in the sample, population size, number in the population. Oh, I see. Population size is mean. Oops, something's wrong here. Just give me a second here. Let me make sure. Anything wrong? 7. See if this works. Guys get an answer, by the way? Just see if this hypergeometric works in Excel. All right, number in the sample is 5. Our sample size is 5. Number in the sample is that. Population size 15. Number of the population. Sample size. Maybe I got it backwards here. Let me see if that's ever tried this before. Nobody got an answer?
Got it.
Not yet. No, I'm still working.
Okay. I'm going to just see how this works here. Number in the population. Population S. Sample size is 7. Number in the sample is 5. Population sample 7. See if this works. 1, 2, 1, 2, 3, 4. Oh, I forgot the. Yeah, it did work. Okay. Cool. Copy. Paste. All right, I just want to see if this works. If it does, then I can show you this. Yeah, it worked. All right. You see if it matches what I got here. Yep, it matched. All right. So, still haven't gotten the answer?
I have an answer, but I'm not sure if it's correct.
What is your answer?
0.3916.
Yeah, that's it. Han, did you get that? All right.
Yeah, I got the same.
Yeah. All right. So you know how to use the formula. That's the key. All right. Now, you have to be careful with using the hypergeometric in Excel because I had it backwards when I first used it and didn't get the answer. I'm going to type it in down here. So do hyper and use HYP and use the one that says hype geom dot distribution. This one here. All right. And it says sample S and then number in the sample. Sample S is is your X. All right. That's the number. That's your X. That's the number that you're choosing out of your sample size. And then the number in the sample is your sample size. In this case, it's 5. All right. Population S is the number of successes. Now, S represents successes. So the number of successes in the sample is X. The number in the sample is 5, right? because you're choosing 5 in this case here. The population success, a number of successes in the population 7. The number in the population is 15. And then I just put false for cumulative, and then I got these probabilities here. And notice the answer for 2 is 0.392. You can do the hypergeometric in Excel also. Okay, which is a good thing, right? I guess as long as you understand what you're putting in.
Okay.
Now the next question says what? In 6.66, what is the probability that at least 3 of them will have advanced training? And therefore, and this makes it easy, you just do the sum of these 3 numbers here, right? This is where this comes in handy, right? So take the sum of these 3 numbers. So if I did that below here, and just did the sum of these 3, at least 3, 0.427 is, I think, the answer. Okay. At least 3. P3 plus P4 plus P5 gives you the answer. All right. That's good. So this is where this comes in handy. This here is the probability that X is less than or equal to, or excuse me, greater than 3, right? Greater than or equal to 3. So I say greater than or equal to 3. Because it does say at least 3, right?
Yes.
Yes. Okay, so that's it. That's your answer. Now, if you wanted to, you could do a binomial in this to see what answer you would get. In other words, you would make your probability of success 7 divided by 15, just for the fun of it, right? You try this as a binomial and see, and then see what you would get as an answer for. You would create your probability distribution. We could try that, right? Let's try it. This is just this is the hypergeometric. I'm going to just type in hypergeome, right? And let's just do it as a binomial just to see if there's much of a difference. Let's try it. Again, you would just okay. And then you would use the binomial here. Binomial distribution. All right. The number of successes would be, of course, above here. The number of trials would be what? It would be this here. And I would put my $sign next to the I, and then probability of success. Why don't I just type in 7 divided by 15? I'm going to assume it's fixed. Just for the fun of it, I want to see what happens here. Type in false for cumulative. Whoa, getting much different answer, huh?
Yeah, that's a big difference.
Big difference. This is your binomial, assuming that probability is fixed. And if we wanted to, if the first question was probability X is equal to 2, right? That's 0.330, and that in hypergeometrics 0.392. It's not too far off, but it's significantly different enough, right? It's in. I would say that this is close to 40%. This is close to 33%, right? Or is 33%. And then the last probability that x is greater than or equal to 3 is the sum of these three numbers. So this would be equal to sum of these three, at least equal to 3. Not too far off. Not too far off. But certainly these probability that x is equal to 0 is way different, isn't it? Look at the difference there. That's where you see the big difference between these two numbers here. And also for 4, right? 4 and 5, you see some difference there. But so this is why we don't want to use the binomial when our sample size is or our population is small. We have a small population here. Only 15, right? Binomial is really to be used for a large population. That's the whole idea. Because in both cases, we have sampling without replacement, right? Sampling without replacement. So for the binomial to work with sampling without replacement, we have to have a large sample size, a large population, large sample, all that. So the probabilities, when they change, they don't change by very much. But with the population is only 15, when somebody's selected, after somebody's selected, the probability drastically changes, or changes enough for these probabilities to be different. Okay, so I wanted to show you that so you could see the difference, right? Sometimes you just have to work the problem out instead of just being told, you know. All right, we have a few more minutes. I want to do a couple more here. 6.67. A producer of copper tubing has found that on average, 5 flaws occur per 2,000 feet of tubing. The tubing is sold in continuous rolls of 200 feet. Did we do this before?
I believe we did.
We did do this one. All right. So this was an example of where Poisson would work. And then 6.68 is once you have the Poisson probability determined, 6.68 is a binomial. You could try that on your own. So 6.67, use your Poisson to come up with the long-term probability, right? For one of these 200-foot rolls of copper tubing. Once you have that, you can use that as your probability of success in 6.68, where you use your binomial. Okay, so do you want to try it on your own, or do you want to move on to, I think we're almost done, I think. Unless that was it. I think that was it. Do you want to try that? See what you get? Oh yeah, there's 2 more I want to go over with you that we didn't do. Let's take a minute. A couple of them. The Poisson should be an easy answer, right? Because 6.67, because it says what's the probability that a randomly selected roll will have no flaws? First of all, what is your lambda in this case here? 6.67. What did you get?
Hold on one second. 0.5.
Right, 0.5. Okay, so 0.5, and you got that because the rate or the probability of a flaw is 5 flaws out of 2,000, right? 2,000 feet of tubing. So the probability per foot of tubing is 1 out of 400, right? And if you have 200 feet of tubing, 200 divided by 400 is 0.5. So that's your lambda. The probability that there's no flaws would be x is equal to 0 for the Poisson. So the only thing you have to put into your calculator is e to the negative 0.5 power. Because everything else turns into 1. 0.5 to the x power is 1, which is 0. At 5.5 to the 0 power is 1, and 0 factorial is 1. You end up with e to the negative 0.5 is your Poisson probability. By the way, you could do 6.67 as a binomial if you wanted to, right?
You could do which one as a binomial?
6.67 you could have done as a binomial too.
Mm.
Where the probability of success is 5 divided by 2,000 or 1 divided by 400. And the number of trials would be what? It'd be 200 because the probability is the number of flaws per foot. And if you have 200 feet, right, then the and the number of trials would be 200. So you could do, it's just easier to do it as a Poisson. It just logically, when you run through it, you don't have to go through those hoops, right? You know what your lambda is, right? You calculate your lambda, and then it's an easy.
Right.
Did you get? So what did you get for your Poisson probability of no flaws?
I got 1.6487.
Probabilities can't have to be between 0 and 1.
Oh, wait a minute. I see what I did wrong. Hang on. I put in 0.5, not negative 0.5. 0.6065.
Right. And Han, did you get that?
No, I use Excel, but it returns 0.
Returns 0
Yeah.
for the Poisson.
Yeah.
Okay. So, if you just did x is equal to 0 here for the Poisson, let's look at on my spreadsheet here. You would put 0 for the first one, and then you would put the 0.5 in for lambda, right? It's the rate times the number of feet. So the rate is 5 divided by 2,000, number of feet is 200. That gives you 0.5, and you put 0.5 in for lambda, you should get 0.6065 when x is equal to 0. We can even.
What do I put in the first number? Like
0. There's no flaws.
Why do I put 0?
Because there's no flaws. X is the number of flaws. And they're saying, what's the probability of having no flaws?
Oh.
Yeah, the rate of flaws is yeah, I'm turning to the side again there. 5 divided by 2,000. And then you multiply that by 200, get your lambda. So it's 0.5, that's your average per foot. No, that's not that's just your average number of flaws in 200 feet, right? Average number of flaws in 200 feet. It's just 0.5. And what's the probability? And then you just put 0 because it says what's probability that a 200-foot roll will have no flaws. All right, and then the 6.68 is literally binomial, where you use the point, use your 0.6065 as your probability of success. And you're finding in 6.68, what's the probability that no more than 3 of the 8 rolls will be flawless? So contractors buying 8 of these rolls, and you want to know the probability that no more than 3 of them are flawless. So the probability of success is the probability of being flawless, which is 0.6065. And you just do a cumulative probability where X is equal to 3. N is 8. All right, so that's your binomial for that question. That's a really good question, right? 67 and 68, to me, summarizes both the hypergeometric and the binomial, when you should use one and when you should use the other one. Or I say Poisson and binomial, not hypergeometric. There's no hypergeometric here. All right. I do want to show you a couple more. Can I show a couple more things? Would that be all right?
Mm-hmm.
Okay. 6.62 is on the previous page. And actually, it's not a bad idea. I don't keep you on too late. Not a bad idea that you do 6.62, 6.63, and 6.64. Did we do 6.64? We didn't do that, right? We didn't do
No.
that, right? All right. I want you to try those 3 as for homework. All right. There's only 3 of them, so if you can have that for me next time. There's only 3. Should, you know, do it tonight, tomorrow night if you want it. 62, 63, 64, pages 201, 202. If you can do those 3, try them on your own. It should be, you should be using hypergeometric a little bit. You should be using binomial a little bit, that sort of thing. I want you to try it, see what you come up with. All right, for those 3 problems. You can try fooling around with the hypergeometric in Excel too. See if you can duplicate what you did with the formulas. All right, sound okay?
Mm-hmm.
All right, just 3 of them, and that'll count as another homework assignment for you guys.
Do you want us to send the answers to you, or you just want us to prepare it for the next class?
No, I want you to send me the answers because I do want to start with the normal distribution next time.
Okay.
Try it. If you're running into any issues, just send me an email and I'll take a look. All right.
Okay.
You can send me an email tomorrow. I'm giving a test at Rowan tomorrow, so I'm not doing any preparation. So if you're trying it and you're running into an issue, I'll check your emails, make sure there's right. Let me know if there's any issues. But I think you should now be able to do those 3 questions, I think, on your own. Because I think you know the difference between hypergeometric and binomial. Should be able to tell the difference. All right. And I think that should do it, I think. Yeah. And you're comfortable with the Poisson now, when to use it and how to use it? You okay with that?
Mm-hmm.
Okay, good. That's it. I mean, if you know how to use those 3 and you know probability distributions in general, you should be able to answer almost any discrete probability distribution question, pretty much. Okay, you should be able to. Just know that there's formulas for the binomial, for the hypergeometric, for the Poisson, that you can use to set up your P of X in Excel. If it's not any of those 3, then you have to, the probability distribution has to be given to you. Okay, it has to be given to you. for you to do any questions with regard to these. And that's good. So I think I'm glad I taught you these additional three. At least the binomial will come in handy later when we do statistical inference, because we'll be using that. All right. There's also information on page 3 about the mean, and actually 200 and 201 about the mean and the variance or standard deviation of each of these distributions. I want to point this out to you. It's a nice summary right here. The binomial, the mean, is n, the number of trials, times the probability of success. They use pi in the book. I'm using small p. Doesn't matter. And the variance is n times the probability of success times the probability of failure. That's the variance. So if you want to find the standard deviation, you take the square root of that. You see that? Yes? Page 200 of your textbook. Yes? Yeah, Hans says yes. Good. So that's a nice summary. And then hypergeometric, the mean is n, the number of the size of the sample, times s, the number of successes in the population, divided by big N, which is the size of the population. NS divided by big N is your mean. And on the next page is kind of a fancy formula for the variance, right? NS times N minus S divided by N squared, and then it's multiplied by this, looks like some sort of correction factor. It's kind of complicated. And then the Poisson, it's actually easy for the Poisson because lambda is the mean. All right, is the mean. Lambda itself is the mean. Now, it says the mean. Now, read this carefully. Poisson, it says the mean and the variance are equal in the Poisson. So lambda is not just the mean, it's also the variance. So if I ask for the standard deviation of the Poisson, you take the square root of lambda. Okay? So everything that you need to find the mean and standard deviation of these three distributions are indicated on these 2 pages. And then they have, of course, the general formulas for the mean and variance of a discrete probability distribution in general, for anyone. Doesn't have to be these three, could be for anyone. And I showed you how to do that in Excel, right? Right, for both. So these 2 pages have everything you need to find the mean and standard deviation for any of these distributions. So you may want to make note of that in case you need it in a test question or whatever. It's right there, and you have access to it during your test. All right, and of course you can always use Excel too, right? To do a lot of your calculations. You can use a spreadsheet and just do everything in here, just like I was doing, right? I could do the same thing. All right, any questions? Are you guys good? And you understand? I'm sorry, go ahead.
I said I think I'm good.
You're good, and Han, you're good?
Mm-hmm.
And whoever else is listening on this video, hopefully the other 2 are going to be listening. What's due on Thursday is 6.62, 6.63, and 6.64. If you can work on it on your own and send it to me before class next time. There's only 3 of them. I would say no more. Please, no, Steve, please, if it takes 2 hours, let me know. I don't think it'll take you 2. I hope not. I wouldn't give it to you if I thought it would take 2 hours. So please, it should, I would guess 15 minutes for these 3 at most. All right. Maybe even less now that, I think you'll be good on it. All right, guys. So anyway, that's it for tonight. I'll stop the recording and you can listen to it again if you like.